Hello, everyone. Welcome back. Today, we'll talk about a different way of thinking about taking the derivative of a function using something called implicit differentiation. So our goal is to be able to use this implicit differentiation to find the derivative of an equation, simply not just a function, but an equation with respect to one variable. Then also be able to find the tangent line of the curve like I had before with other derivatives at any point using this technique. So here's the idea. So let's say you have an equation. You need to take the derivative of the well, I'll just go ahead and let's see. So the idea is you have some function or equation, and basically you need to find the instantaneous rate of change of that equation at some point, or any point. So let's come over here and just think about our first example. This example will do. And let's just start with something you should be familiar with. X squared plus y squared is equal to 1. Okay. So if you remember, that's the equation of a circle. Okay. With centered at the origin and a radius of 1. So if we graph that on Desmos, let's go to Desmos. And the nice thing about Desmos, we can actually graph equations on Desmos. We just do x, oops, wrong thing, x squared plus y squared equals 1. And there it is. We can actually graph equations with Desmos. So if we zoom in a bit, okay, there's our circle. So once again, centered at the origin and a radius of 1. Now, what if we wanted to find the instantaneous rate of change at any point along this circle? And once again, of course, that's going to be the slope of the tangent line at any point of the circle. So the way we do that with an equation like this, or something like this, or any general equation, is called implicit differentiation. All right, so let's come back over and talk what that means. So sometimes we need to find the instantaneous rate of change of one variable that is given as part of an equation with two variables. In this case, the two variables, x and y. So in this case, we can take the derivative of the equation, we say implicitly, we assume one variable is a function of the other. Okay, so we could assume that, for example, y is a function of x, or x is a function of y, and that will then allow us to take the derivative of the entire equation and then find the derivative, okay, of, for example, y is a function of x, or the other way around. So as I say next over here, if we go back on the left, for example, of equation with x and y variables, we can assume that y is some function of x, take the derivative of the equation with respect to x, or do it the other way. We can also assume that x is a function of y, either way, and take the derivative with respect to y. And what we'll do is we're going to use the chain rule like this. So we have this equation, y equals f of x. So y prime, the derivative of that function of y is, of course, the derivative of whatever the function of x is, then times the chain rule, then the derivative of y with respect to x. And the same thing here, we just switch variables x and y to make y our independent variable. So our rule, or our goal, then, is going to be, it says assume to find the derivative with implicit differentiation. We're going to assume that y is a function of x, like this, as we just said. Take the derivative of the equation, take the derivative of each part with respect to x, and also use the chain rule to get an expression dy over dx. And then we're going to solve the equation for that dy over dx. And then it says if you assume that x is a function of y, if you want to do it the other way, just repeat the same steps, these same three steps, just switch the x and y's. Let's come back over here to the right and take a look. Let's say we want to assume, all right, so first we're going to assume, I'll say y equals y of x, meaning that y is some function of x. Okay, so if I just rewrite this, x squared plus y of x squared, plus its quantity squared here, okay, is equal to 1. Let's put that in parentheses right now to make it clear. I was talking about this y of x, whole thing squared, okay? Now, take the derivative, oops, misspelled that, derivative, and just abbreviate that, take the derivative with respect to x, assuming x is our independent variable. Okay, so to start down the line, so basically what we're going to do then, write that symbols looks kind of like this: d dx of x squared plus y of x squared. And so once again, since it's an equation, what I do to one side, I have to do to both sides. Okay, Now, since it's simpler, let's actually start with the right side. So remember, this is a constant over here. Doesn't just have to be a constant on that side, but it is here. Of course, that then is going to be 0. Now, remember, since this is what's called linear, I can take the derivative of each one separately. So the derivative of x squared, and let's go and write it out anyway. So the first one, make sure this is clear, and plus the derivative with respect to x of y of x quantity squared. Okay, so the derivative of x squared, of course, is 2x. The derivative of something squared is 2 times that something to the first power. And actually, I'll just get rid of the parentheses. Okay, so this is y, basically y squared. The derivative of y squared is 2y. Then times the derivative of y of x is we're going to call it, because we don't know exactly what y is, how it's necessarily related to x. We just know, though, that using the chain rule, the derivative of y itself is going to be dy over dx, and this is equal to 0. Okay, so once again, what we did, to add this equation, we assumed, in this case, although these are both essentially independent variables, we assumed that y was some function of x. We don't know what it is, but just some function of x. We took the derivative of both sides of the equation. I got this point. So the derivative of 1, of course, is 0. Derivative of x squared is 2x. That's normal. And here we have y squared. So the derivative of that is 2 times y, or 2 times whatever this is. Then the derivative of y with respect to x, using the chain rule, is dy over dx. Okay, so now what we want to do then is solve for dy over dx. So this is an equation, solve for that. Let's subtract 2x on both sides. So we have, and now I'm just going to call it, I'm going to drop the of x part, just call it y. So 2 times y times dy over dx is equal to negative 2x. Okay, then divide both sides by 2y. And then finally, we get that dy over dx is equal to negative x over y, because the 2's would cancel out. I can put them in here, just to cancel out, and so that's going to be negative x over y. So what that does, that gives me this expression, x over y, negative x over y, gives me, if I plug in an x and y, it gives me the rate of change of this, that function, instantaneous rate of change of this circle, this function, at any point. Okay, if any point I pick, it could be here, anywhere I want, all right, it's going to give me the instantaneous rate of change at that point. Okay, if I plug in the x and y, it will tell me what the slope of the tangent line is at that point. Let's do one example of that. What we're going to do is let's find the slope of the tangent line at this point. We'll just use decimals on the circle. This point approximately is on the circle, 0.5 and 0.866. Okay. So dy or dx at that point, and this notation some people will use for this, 0.5, 0.866. This means we're taking the derivative at that point. Okay. And so that's going to be negative x, which is 0.5, over y, which is 0.866. And that came out to be, that's rounded 3 places, so negative, I was rounded 2 places, negative 0.58. Okay. Now, first off, let's make sure that does at least make sense so far. Let's go back to that point is right about here. If I can get close to it. Okay, there we go. In fact, let me just go ahead and I can also plot points of decimals. Let's just type that in. 0.5 and 0.866. Okay, and label it. Now, notice the slope of that tangent line should be negative, and it is. Okay, it should be negative. All right. So what we do now is you can find the equation of that tangent line and see if it does actually touch this. Using the value we found, if it actually does touch that point, touch the graph at just that one point. It's negative. It should be negative, and it is. That doesn't tell us everything. Okay. So find the equation of the tangent line. Oops, I don't know why I did that. Once again, at that same point, at the point 0.5, no, 0.5 and 0.866, okay? And so we want to find, what we want, of course, is y equals mx plus b. We just found that m is equal to negative 0.58, okay? So we have so far is y equals negative 0.58 plus b, x, you get the x, okay? Now, let's plug in the point. We need to find b, okay? So y is 0.866 is equal to negative 0.58 times 0.5 plus b. And then if we solve this, this is approximately, b is equal to about 1.56. Okay, so our equation is y equals negative 0.58 x plus 1.56. Okay, let's see if that's true. Let's see how well that is. All right, so go back here. Y equals negative 0.58 x plus 1.16. Yeah, looks pretty good. All right, so see this line touches it at just that point. All right, so that's the slope of the tangent line. And we can do that for any point on the circle. We can just use that equation then to find the slope of the tangent line. Okay, one thing to make note for, of course, right here, actually the slope of our tangent line would be a vertical line, which would be undefined, and that would also make sense because we look, remember, at our derivative, implicit derivative, then x over y, at that point, y would be 0, and so that'd be undefined, which makes sense. Okay, let's do one more thing with this one. Let's do one more. So here what I want to do is let's find, I want to say now, show you how this works. Let's now assume that x is a function of y. So x equals this, okay? Now what we do now then is let's find essentially dx over dy. So we're going to repeat all the same steps we just did, except this time we're going to have is the derivative of x with respect to y. So reverse it, see what that looks like, okay? So that means our equation was x squared plus y squared equals 1. So we have x of y is a function of y squared plus y squared is equal to 1. Now what we're going to do then is take the derivative with respect to y. So just the same as it did with x, but now we want to think of it, take the derivative with respect to y. Okay. And once again, what we're going to do then is take the derivative of both sides. With respect to y. Okay. Once again, this side, this is a constant that's going to be 0. Okay. Over here, we take the derivative of each part. Oops, wrong thing. Hang on. Okay. And you'll see it's very similar to what we got in terms of x. Okay. So here, let's actually do this second part here first. The derivative of respect to y of y squared, of course, is just going to be 2y. Now over here, like we saw before, we have something squared. The derivative of that is 2 times a something. So 2 times x of y. Okay. Then the derivative of x with respect to y is going to be dx over dy. Okay. And now, just like we did before, solve for dx over dy. Okay. And once again, I'm going to drop the parentheses with a y here. So we'd have 2x times dx over dy plus 2y is equal to 0. And now we're solve for dy. So subtract 2y from both sides. We have 2x dx over dy is equal to negative 2y. Divide both sides by 2x, and we get that dx over dy is equal to negative y over x. So if you don't remember what we got before, we took the derivative of this with respect to x, was negative x over y. Now take the derivative with respect to y, and it's very similar, except it's now negative y over x reciprocal. Okay, and also in the same way, if you wanted to find that would give you the slope of the tangent line at any point on the circle, but then if you did it that way, then you actually have to think of it as a linear equation in terms of x. It'd be like x equals y, x equals my plus b. We're not going to go through that, but get the idea. So that's how that works. We can think of it as taking the derivative of either of the entire equation with respect to either variable. Okay. Let's look at another one. Okay, number 2. So here is our equation. xy is equal to 7. So let's go to Desmos and let's graph that. Just kind of get an idea what it looks like. Okay. Now, actually, I think I'll just open up another Desmos window since I want to erase all that. So x times y is equal to 7. Okay, so we get a function curve looks like this. I want to take the derivative. Okay. Now here, from now on, we'll just assume everything, we'll just assume y is a function of x. But just remember, as we saw before, we can always do it the other way. So once again, we're going to assume that y is some function of x. Okay. And so that's going to give us then x times y of x is equal to 7. Okay. And then take the derivative with respect to x. Okay. So take the derivative with respect to x. Okay. So okay. Once again, it's probably easier to start with the right side because that's just a constant again. So of course that's going to be 0. Now here we actually have to use the product rule, okay? Because assuming that both x and of course y are also functions of x. And so remember how the product rule works. So we take the derivative of, in fact, let me actually move this over so I have plenty of room. Just squeeze it all in there, okay? So there's going to be the derivative of the first function of x times just y of x. And so that's going to be derivative of x is going to be 1 times y of x. I'm going to drop the of x part, just call it y. Okay. Then plus x times the derivative of y. So actually, since this is simply just a y, think of just like x is to just be 1, the derivative of just something to the first power, just that something. Okay. And then the derivative with respect to x is going to be dy dx. Okay. Now, let's kind of simplify this. So we have y plus x times dy dx. All right, is equal to 0. Okay. Then, of course, solve for the derivative dy over dx. Okay, subtract y from both sides. We have x times dy over dx is equal to negative y. And finally, divide both sides by x, and we have dy over dx is equal to negative y over x. Now, first off, don't be confused. This may look like what we've got before, but it's not. So let's look back what we did get before. So with our circle, because obviously the graph we had is not a circle. Circle, what we got for dy over dx was negative x over y. Okay. Now, also, if we solved it for dy over dx over dy, if we solved it for y, we got negative y over x. But here, this is dy over dx equals negative y over x. Okay, it is different. All right. Now, we want to find also from here, we want to find the, and basically at this point, then you can do exactly the, actually change my mind, exactly the same thing you've done before. You know, if you want to find, if you have a specific point on that function, you can then find the equation of the tangent line by plugging it in, and also as we did before, then find the slope of the tangent line, then also find the equation of the tangent line. Okay. Next one, number 3. Okay. This time, let's say we have this equation. E to the xy is equal to 2y. Okay. Let's go back to Desmos and see what this looks like. I'll just turn this one off. So this time we have E. Now, actually, if you want to raise something within Desmos, you can put parentheses. If you don't, if I just do x, then y. Actually, well, it actually did. Okay. But you can always use parentheses if you need to, just to make sure it doesn't, keeps it in the exponent. Okay. Equals 2y. All right. If you notice, since we have a function of x and y like this, you know, this may not be strictly a function, like a circle is not. But that's the graph we get. Okay, so the same way, if I want to trace any point on this graph, any point on this graph, I can also find the slope of the tangent line to that graph. Let's go back and do that then. Okay, so once again, we want to assume that y is some function of x. Okay, and so that's going to be e the x times y of x is equal to 2 times y of x. Okay, this time we have 2 functions of y. So, and once again, anytime we see a y, doing the chain rule, we're going to have a dy over dx. We actually have 2 dy over dx's. We'll have to get those together. We'll talk about it here in a minute. Okay, so let's actually, this time, once again, let's actually start on the left side. Well, first off, we need to take the derivative. Once again, this is the derivative with respect to x. I'm just writing that. So this is going to be the derivative with respect to x of both sides, e to the x times y over x. The y to the x is equal to the derivative with respect to x of 2 times y of x. Okay. Now, once again, let's do the right-hand side first. So, of course, we pass through the constant. The derivative of just y is just going to be basically just dy over dx. Of course, the derivative of y, it's just like the derivative of x itself would be just 1. So that's going to be 2 times dy over dx. All right. And here, we have to use the chain rule a couple times. Okay. So remember, the derivative of e to the something is the something. And so that's going to be e to the x. Now I'm just going to drop the respect to x part. It's called ey. Okay. Now, the chain rule says then I have to take the derivative of the inside function, the top part, x times y. And that I actually have to use the product rule. So just take your time with ones like these. They have, just make sure you take care of everything. Okay. Actually, we already saw this just a minute ago. This would be just like what we saw in the previous one. Is x times y. So we're just like that. Okay. So if we take the derivative of x, which is going to be 1 times y of x, and I'm going to drop the respect to x part, okay, plus then x times the derivative of y to the x is just going to be dy over dx. Okay. Now, basically, calculus part is over. We just have to kind of simplify this and solve for, get the dy over dx by itself, one expression for dy over dx. Okay, so first let's clean it up some. So we have e to the xy times in here, we're going to have y plus x times dy over dx And then we're here, that's equal to 2 times dy over dx. And once again, we're solving for dy over dx. We have two of them. What we have to do is get them both on the same side. So we need to kind of distribute, multiply through. Let's distribute the exy here. So if we multiply it by here, this is going to be y times exy plus, and it doesn't matter what order I put this in, but this part of it, x times dy over dx times e to the xy is equal to 2 times dy over dx. Okay. Now, once again, we want to get the dy over dx's together and kind of everything else on the other side. So let's do this. Let's subtract this term from both sides. Okay. So we still have this term left on this side, y times e to the xy. Okay. Then we're going to have 2 times dy over dx. Then we said we're subtracting this term from both sides. So minus x times dy over dx times e to the xy. Okay. So now we got the dy over dx terms on the same side. So now what we need to do is actually want to factor this. We've seen something kind of like this in algebra before. Factor the dy over dx, the common factor out of both. So my left is still the same for right now. Y times e to the xy is equal to, so if I take a dy over dx out of both, see what I have left. What I have left is 2 from this one, and minus, and here what I have left is the x and the e to the xy. Okay. All right, and we're almost there. So last thing we need to get this by itself is divide both sides by this term, 2 minus x to the exy. And I'm also going to turn this around. Let's go ahead and write that out. So 2 minus, oops, x, and then the e to the xy. Divide both sides by that. So these cancel out. What we're left with then is this. So dy over dx is equal to y times e to the xy over 2 minus x times e to the xy. Okay, so that gives the slope of our tangent line. Once again, it's also called implicit because basically I'm assuming that y is a function of x. And also, just like the other one, when we started with the circle, you could also assume that x was a function of y as well and get a somewhat similar expression. Okay, and so the same thing here, we can do with this as well, if you wanted, is you can actually then find, let's go back to our graph of this function. Any point on here, find the slope of the tangent line to that point, and then graph the tangent line at that point in the same way we did before. Okay, let me check something. Let's do one more. Also, let me make sure I have enough. Should be enough. I have enough room. Yeah, let's do one more. Okay, and this will be number, I don't remember, number 4. Okay. This time, let's say we have this expression. So this is equation, the square root of x plus y squared is equal to the sine of y. Okay, so once again, like I did before, let's go back to Desmos and just graph this, kind of get an idea what it looks like. I do a square root, just type SQRT, x plus y squared is equal to the sine of y. That's interesting. It looks like we have a couple of gaps here, maybe where it's not defined, or basically where it may become since we have a square root, it's probably where it becomes potentially depending on the value of x and y, it becomes imaginary. So it's kind of a strange graph. But here we're not going to worry about that right now. We're just going to see if we can actually then find the derivative of this. Okay, implicitly. So let's go back and take a look. All right. So instead of rewriting all the words, let's just say same as before. So let's just say I'll just say assume, once again, I will say this part, assume that y is some function of x. Of course, you could also assume x is a function of y, but we'll just keep doing it this way. All right. So now, in fact, what I'm going to say that, but I'm not gonna write the y this way as before, just so it doesn't do as much writing, kind of clutter things up. All right. So once again, let's take the derivative with respect to x of both sides. Okay. Now, actually, I'm going to go and do one thing right now. Let me change this. Remember, this the square root is the same as the 1/2 power. A lot of times the derivative I like to do that because it's easier to work with. All right, because this basically then if you do this 1/2 power, you don't have to think about it in terms of a separate rule for radicals. Just think of it as basically a fractional power. All right. So this time let's just go straight across. Okay. So this is also the chain rule. We have something to the 1/2 power. The derivative of that first is the number out front, 1/2 times the something, x plus y squared, okay, minus this minus 1, or negative 1/2, okay. Then the chain rule again, what's on the inside, okay. The derivative of x is just 1 with respect to x. The derivative of something squared is going to be 2 times a something, okay. It's like, does x squared to be 2x, so 2y, it's 2y. Then the derivative of y is dy dx. Once again, the chain rule there. Okay, so take a minute, stop, you need to look at that, make sure that makes sense. So we did the derivative of the 1/2 of something first. Then for the chain rule, did what the derivative of the inside of it. So derivative of x was 1. Derivative of something squared is 2 times that something. The derivative of y is dy over dx. And then over here, the derivative of sine of something is the cosine of that something, cosine of y. And then once again, the derivative of y is dy over dx. Also make sure it's clear we're not doing the cosine of this, just the cosine of y. Okay. Once again, solve for dy over dx. Now here it's a little more complicated. Let's clean things up a bit using algebra. Let's get rid of the negative exponent. All right, so here we're going to have 1 over 2 times x plus y squared to the 1/2. We'll write that as a root here in a minute as well. We still have this is basically unchanged, 1 plus 2y times dy over dx. And here, this side's also unchanged, so the cosine of y times dy over dx. Okay. Now, if you notice, like we had in the previous example, we need to get these dy over dx terms together. And we essentially do the same thing. So remember, the last one we had something like an exponential expression. Here, we distribute it and do the same thing. Okay. So give a pain, be a fair amount of writing, but the procedure is exactly what we did before. All right. So distribute this term here times 1. That's easy. That's going to be 1. I'm also going to put this back in terms of a radical. So the 1/2 power is going to be the square root of x squared, x plus y squared, okay, times 1, plus I'm going to have 2y over this 2 times the square root of x plus y squared, then times dy over dx is equal to the cosine of y times dy over dx. Okay, so all I did was just distribute this term, both of these. Now, I'm also going to do something else that's going to make this a lot easier to work with. Okay, let's go back and take a look. Our equation we start out with said the square root of x squared plus y squared is the sine of y. Okay, we can use that here, all right, because that's something that's been established. What I can do is I can replace square root of x plus y squared with the sine of y. Okay, so get rid of the square, it's going to make it a little bit easier to work with. So this is going to be 1 over 2 times the sine of y, plus, and also here if you notice the 2's will cancel out. And so here I'm going to have y over the sine of y, still times the dy over dx. And that's equal to the cosine of y times dy over dx. Okay. Now, one more thing. Remember here, this part is also kind of optional, but I'll go ahead and do it. So remember, 1 over the sine is cosecant. And so I can write this as basically cosecant of y over 2 plus y times the cosecant of y times dy over dx is equal to the cosine of y times dy over dx. Just makes it a little bit easier to work with. Okay. All right, let's keep going. All right. So we're going to get the dy over dx terms together. So let's subtract this term from both sides. And so on this side, we have the cosecant of y over 2 is equal to the cosine of y times dy over dx minus y times the cosecant of y times dy over dx. And as we did in the previous example, we want to factor out the dy over dx. Okay, our left side stays the same for now. Cosecant of y over 2 is equal to dy over dx times cosine of y minus y times the cosecant of y. Okay, and then basically just one more step, divide both sides by this. All right, so finally what we get for our derivative, our implicit derivative, is dy over dx is equal to the cosecant of y over 2 times the cosine of y. This is in parentheses, the cosine of y minus y times the cosecant of y. And that is our derivative, in this case entirely in terms of y. Okay, now that was a bit of a pain, obviously, but at the same time what we got then is, look back at our graph, which also is a strange graph. And we'll say it's partly because where this becomes, it's not including it, but graphing it correctly, at least where it becomes imaginary here, we have the square of a negative number. But it looks something like that. Okay, then anytime we want to find the slope of the line, any point here or there, that would give us the slope. Slope of the tangent line, and we also can find the equation of the tangent line, just pick a value of y. Okay, so let's review what we learned so far today. So what we learned then is another technique of differentiating called implicit differentiation. So if we have an equation like we start out with, the circle or something like that, okay, and we need to find the instantaneous rate of change at any point along the graph, we can assume that one variable is a function of the other variable. It doesn't matter which one we pick. And then basically take the derivative with respect to what we think of as independent variable. Once we do that, we get an expression for the derivative, often in terms of both variables. Sometimes true, sometimes not, as we did here. And then we do the same thing, have that instantaneous rate of change. We do the same thing with that. We can find the slope of that will give us the slope of the tangent line, and also help us find the equation of the tangent line. And once again, also give us, said, the instantaneous rate of change at that point, which is useful in other ways. Thank you. Have a good day.